So, let me start with the first topic, that is solar energy conversion and silicon solar cell. So, in this topic I will cover the importance of photovoltaic cell and all the basic equations which is required for a junction solar cell, some of its challenges and its application in various areas of science and technology. So, let me start with some of the important application of a solar cell. So, we know that the solar cell is basically a device which gives us energy, and it takes energy from sun, and then this energy of sun gets converted to electrical energy in the solar cell device. And if we can use this energy and can apply this energy for various devices which are important for both domestic as well as for common usage, then there are definitely some important areas where the solar cells are important. So, if we consider a solar farm, these days we see that there are large number of solar cells which are connected in a panel, and then these panels can produce lot of energy, and this energy can be converted to a energy which is required for a power station, and that it can be coupled to grid also, and therefore, this energy can be used for general purpose and also for electricity. Second is, we know that the remote areas where we do not have the conventional electricity, however, we have enough sunlight in various places of different countries, different regions, enough sunlight we get. However, we do not have much electricity in those regions. So, what one can do, one can use solar cell or small solar panels in the roof, okay. And also one can use small appliances like solar lantern, solar torch, where they get energy from sun, gets converted into electricity, and then it is stored. This energy is stored and this energy is used. Another important use is the satellite system. We know that in satellite, which are actually the vehicles which move in the outer space, there is no source of energy as such, the conventional energy. So, one way is of course, the chemical energy or stored batteries, and another way to use the solar energy. So, these days it is becoming very popular and it is being used in various satellites, and lot of program of space program are there, where various countries they are trying to put the more and more solar cells as energy source of the satellites. Another important thing is that is the application of solar cell is that one can have localized solar panels which can be used for say traffic signal, or an application which are very localized, maybe in some handset, in mobile, and therefore, the importance of solar cell and photovoltaic technology is not only restricted to the the electricity distribution in a large area, it is actually it covers a large application to a small household application to a domestic use to personal use. And therefore, it is important to know that what are the materials that one should have to make good solar cell devices. Okay, so if we look at the roadmap of solar cell or photovoltaics, we can say that almost by 2050 almost 11 to 12% energy or the electricity or the power will be generated using different solar cells, and that will be used in various applications as I have mentioned just now. So, what are the challenging issues? The challenging issues are, see, there is enormous energy in sun and it radiates huge amount of energy, but are we capable enough to to convert this energy from sun to our useful electricity? Is it possible to convert the entire energy what we get from the sun to make an electrical power appliance or as a generator? Not precisely. The amount of energy which comes from sun is most of them are lost, because the kind of technology which we have at this moment is not capable enough to use this energy or convert this solar energy to the electricity. So, because the conversion of light energy to electricity depend on the material which we use. So, how does it happen? So, suppose light is falling on a particular material, how it will give electrical energy, how it will be converted to voltage. So, there has to be some mechanism which essentially makes the use of the energy conversion. The mechanism is that in the material, when the sunlight falls, some sort of charge carriers are generated. So, once the charge carriers are generated, then this charge carrier has to be transported. So, suppose in a material I generate electrons and positive ions by shining light on it. The next step, we should be able to transport these charge carriers, that is electrons and positive ions, to outside circuit, so that we can have a current in the outside circuit, and if we connect a load in that, then we get electricity. So, conversion of solar energy to charge carrier and from charge carrier movement to electrical energy is the most important challenge. So, what are the things comes in that? We cannot randomly choose a material, to just put in front of solar energy, and we think that there will be useful voltage which will come out from that. That is not possible. There has to be some specific material properties which actually play the most important role in this entire conversion process. So, what are the materials? If we look at or to begin with, the one of the most important material which has been studied extensively is semiconductor material. Okay. So, what is the advantage of semiconductor material? The semiconductor material, the advantage is that the band gap of semiconductor material is such that it can absorb light easily. If we consider metal, metal does not have a band gap. That means, the energy gap between conduction band and valence band one can say is 0. But in semiconductor, the typical range of energy, band energy, is from say a fraction of an electron volt to 2 to 3 electron volt, even more than that. So, it is a huge energy range which one can cover when one uses semiconductor, and therefore, it can use a broad spectrum of light to get absorbed in the material. So, the first point is the absorption. There has to be a strong absorption of light or strong absorption of photons in the material, and that is basically decided by the band gap of the material. The second point is, of course, when light falls on a semiconducting material, then electron goes from valence band to conduction band. There is a transition. Okay. So, this transition actually allows as its next step to flow these electrons which came to conduction band to the outer circuit. So, the second point is transport. Okay. So, now let us see few important solar cells which people have studied, and they are basically divided in various generations. We call different generations of solar cell, and this generation actually come from the material which we use. Okay. So, now we will start with the first generation solar cell. So, what is first generation solar cell? First generation solar cell is basically a solar cell made up of silicon. Why silicon? The reason behind this is that when we talk about the electronics industry, silicon is a material which is properly known to all researchers, and also it has been technologically used in various fields, and then entire electronics industry is based on silicon, although there are nowadays there are some other material, wide band gap semiconductor, but silicon is most widely used. So, it is a known material, although silicon has a band gap of 1.1 electron volt, which is not an appropriate band gap for absorbing all kinds of photons of solar spectrum, and its transition is also indirect. However, because of its important properties and the known way to fabricate it and use it in the devices, people have started first generation solar cell with silicon. So, you can see the first generation solar cell which people talk about basically wafer based. So, where they use monocrystalline silicon, they have used polycrystalline silicon, and then of course, they have started using thin film of amorphous silicon also, and that actually leads to another generation, that is called thin film technology in solar cell. So, what was the requirement of a thin film technology or the second generation solar cell? So, if you look at the second generation solar cell are basically the compound semiconductor solar cell. There are various compound semiconductor solar cell. Why a compound semiconductor is required? Why thin film is required in solar cell technology? Because the silicon solar cells, they are all wafer based. So, if you just look at a silicon solar cell which is there in your laboratory, you will see that it is made on a wafer, silicon wafer, and the thickness of this wafer is 300 to 400 micrometer. Why 300 to 400 micrometer thickness is required? This is because otherwise we will not get enough absorption of light in silicon. And another problem is that the transition of silicon is indirect transition. Okay. Now, if we use the compound semiconductors like cadmium telluride, like gallium arsenide, these materials they have direct band gap, they are generally direct band gap semiconductor and they are wide band gap. So, if we take cadmium telluride, its band gap is around 1.5 electron volt. Therefore, it can absorb light more efficiently as compared to a silicon wafer of same thickness. Okay. So, for silicon, if we need 200 to 300 micrometer thick wafer for same amount of absorption in a compound semiconductor like CDT or gallium arsenide, we need much thinner material which can do the same job. And therefore, the second generation of solar cell was the compound semiconductor based and thin film based solar cell. So, which we will cover in the second topic of my lecture. Third generation is, if you see that cost is always a very important issue in solar cell. So, if we consider silicon solar cell, which we will see that the fabrication of silicon solar cell in my next lecture, you will see it is very heavy and very the costly techniques which are involved to make a silicon wafer and to make a silicon solar cell and to make a silicon solar cell panel. So, one has to see that how to reduce that cost, and that is actually one important shortcomings which actually does not allow silicon solar cell technology to grow in all ways. So, in order to reduce cost, people have started thinking about completely new material and little bit of new configuration of solar cell, and these are third generation solar cell, which are dye sensitized solar cell, which are quantum dot sensitized solar cell, which are organic photovoltaics, which are perovskite solar cell, and also the hybrid or tandem solar cells. So, these are all important generations of solar cell, which we will go through as we learn more in this course, but we will start today with silicon solar cell. So, in silicon solar cell, if we look at the starting or the way people have started thinking about developing a silicon solar cell, we have to follow a little bit of chronology in that. So, if you see that the chronology how people have started working on that. So, it has started way back in 1839, and Edmund Becquerel was a person who first discovered the photovoltaic effect. And in 1883, people realized that this photovoltaic effect can be properly utilized in silicon. So, 1883 the first photovoltaic effect or the first silicon based solar cell was discovered. And in 1916 there was the famous discovery which is known as photoelectric effect in physics. In photoelectric effect, in fact, what happens when light shines on a material, the electrons are generated, photoelectrons. So, that was nicely explained by Albert Einstein, and he has also received Nobel Prize for it. So, this is a part of the activity which was going on with the as the result of light and matter interaction. So, if we look at 1918, people have started growing the single crystal of silicon, which is extremely important, because the growth of silicon single crystal and then wafer is a very important stage to develop a full silicon based photovoltaic cell as well as the silicon based photovoltaic panel. 1954 Bell Labs in America, they first demonstrated a solar cell with an efficiency of 4.5%. And then after that in 1960, 14% efficient silicon solar cell was demonstrated by Hoffman Electronics, and then 1970s people have started large scale use of silicon in photovoltaics technology. So, now let me show you this particular important thing in the solar cell, because the point which I made that why we cannot use the maximum energy of sun which is falling on earth as electricity, why we cannot convert. So, if you look at this particular figure, you will see that the x axis, this is basically the band gap, and this is maximum efficiency of solar cell. So, if you look at this curve, you can see corresponding to different band gaps, we have different efficiencies of solar cell. So, silicon falls somewhere here. If you see, the silicon is here, silicon band gap is 1.1 electron volt, and gallium arsenide, which is a compound solar cell or compound material or wide band gap material, it falls somewhere here, and both of them show quite high efficiency in terms of theoretical calculation. Of course, practically also people have shown a relatively higher efficiency for both silicon and gallium arsenide. So, now if we come to other compound solar cell like CIGS, CDT, etc., then their efficiency is generally less, although their band gap is good enough to absorb more light, and they are used in thin film solar cell. So, now the question is the why solar energy is lost, 67% of solar energy is lost. So, if you look at this figure, you can see that when light falls on the material, then the electron can go from this place to this place. There is a transition, that is from valence band to conduction band, then it falls back. Okay. So, if the energy of the incident photon is less than this band gap energy, then they get transmitted. So, you lose this particular photon because it is transmitted, its energy is less than the band gap energy. And if its energy is much higher than the band gap energy, this case, then there is another loss which is called thermalization loss or loss in excess energy. And therefore, it is important that the material band gap should be such that it falls almost within the energy range of incident photon. So, therefore, the transmission loss can also be minimized and the thermalization loss can also be minimized. Now, again you see this particular plot which people have done work on various generation. So, if you can see this the silicon one, this is a green one. So, if we start looking at the year, that is from around 1940, 1950, and now the stage where we can see an efficiency of around roughly, you can say an efficiency of close to 26 to 27%. Okay. This is the efficiency which one can have when you use the silicon. So, you just follow this green line. Now, you come to another thin film solar cell which is wide band gap solar cell, that is CDT. CDT is this one, you follow this. the orange one, you see this its efficiency, it has started little later if we look at the year, but its efficiency is much less as compared to silicon, somewhere around 21% or so. Now, the red one is the perovskite solar cell, which actually came up much later. I will say that just it has started 10 years or 12 years before. However, it shows a great potential. So, if we follow this red line, here you can see that there is a sharp increase in energy, okay, in efficiency, sorry. So, it can almost reach 30% of efficiency, that is this one. So, there are a lot of potential in this third generation solar cell or the perovskite solar cell. Now, the question is it enough? Is it a limitation that I use a single material like silicon or I use a compound material like CDT, but I do not see an efficiency which I am looking for. Somewhere it is stopping around 30-31% theoretically and experimentally also very research level somewhere very close to that. So, people thought of combining solar cells, they call it tandem solar cell. So, if we use a perovskite solar cell as well as a silicon solar cell, the question is what you are going to gain. So, in one particular solar cell, suppose I use perovskite solar cell at the top and then I have a silicon solar cell at the bottom, and light falls on this, what will happen? What I will gain? What I will gain is that this band gap of perovskite solar cell is such that it will be able to absorb high energy photons, and this one its band gap is such that it will be able to absorb low energy photon. So, now if I have a hybrid structure or a tandem configuration of perovskite as well as silicon, then what I can get? Absorption of photons which are high energy in top layer, that is on perovskite, and absorption of photons in silicon which are low energy. So, that means I can cover a broad range of electromagnetic spectrum or a broad range of solar radiation. So, now let us follow this blue line. So, look at this blue line and see where efficiency is going up. Okay. So, it has started this concept of the tandem or hybrid solar cell, it started somewhere in 1980s, but recently the research has gone up so much and people see that there are a lot of promises, because you can absorb lot of light or photons of various energy ranges in this hybrid structure, and therefore, you can see a huge rise in efficiency. Okay. So, that is extremely important, and therefore, we will discuss this type of solar cell also in future, combining silicon and perovskite solar cell. Now, let me again show you that this is a configuration of solar cell. So, what is the incident light? So, if you look at this spectrum, this is the typical solar spectrum, this is wavelength versus spectral strength, and what people talk about, that is AM 1.5 as standard solar radiation. What is AM 1.5 as standard solar radiation? It is air mass 1.5. This is a standard notation. This corresponds to a power density of 1000 watts per meter square. So, that is quite a lot of energy which is falling on the earth. Okay. So, now when you use this spectrum, okay, and then you have a material which just now I have shown. So, how do you combine this? That is called photovoltaics technology. So, if we look at the conversion steps, so just look at the conversion steps. So, what we need? We have to select a suitable material which can convert this particular energy of sunlight to a useful energy in terms of electrical voltage. Okay. And then how it does? It generates charge carriers. So, there should be efficient generation of charge carriers, and then this charge carrier should be collected outside. So, there should be an efficient collection of charge carriers, okay. And then you have to have a better circuit where you can flow these charge carriers and generate electricity. Okay. So, let me just go to this junction again. Okay. So, this is a very fundamental thing which we all know. So, you just look at this junction which I was discussing. So, this is a semiconductor junction which is formed when you have an n type and p type region. And how does it form? When in n type semiconductor and p type semiconductor are fused together or a junction is formed, then the majority charge carriers of one particular side flows to another particular side, that is from n region to p region, and from p region to n region the opposite charges flow. Okay. And therefore, at the middle there is a region which is formed, which is depletion region, and this depletion region is basically a region which one can also a little bit modify or tailor. One can change the depletion region width, okay, play with the depletion region width. But what is more important is that in the depletion region, if you just should see the potential varies in this manner. So, in the depletion region there is a built-in potential which is formed. So, what is the importance of built-in potential? So, if you see this equation basically shows the built-in potential. The built-in potential or the built-in electric field, which is extremely important in solar cell, because this is the electric field which actually drags the charge carrier and takes away from the junction. So, higher and higher built-in potential or higher and higher built-in electric field we have in the junction, better and better charge flow efficiency we can see in the solar cell. Okay. So, what we require a good or healthy depletion region with a good built-in potential. So, this is actually the way, if you look at the energy band diagram. Okay. This when photon falls, how the charge carrier or what is the transition of charge carrier from valence band to conduction band. Okay. So, what essentially happens that an electron hole pair is generated which flows in the circuit. Okay. So, now I just want to draw a little bit of small electric circuit with this particular concept. So, what I do? I consider this I s here left hand side, you can see this one. This is a photo generation charge carrier source. Okay. Why photo generation charge carrier source or the current generation source, you can say this because when light falls it actually gives an electron and positive ion charge carrier or electron and positive ion pair. So, this is a current source I can consider here, and then this one is a diode, as I mentioned that you have an NP junction. So, this is a diode, and then I have a load here. Okay. So, this is the circuit when we talk about in terms of electrical circuit of the process which I mentioned. Just now, that is the physical process is now converted to electrical process. So, now we have a circuit. So, we have to see what are the the mathematical equation, then one can set up to analyze this circuit. So, if you look at this the mathematics here, before I go to the mathematical equation, let me just tell you one important thing here. See this, we start with a junction with p-n junction, correct, and then the charge carriers are generated in the junction, okay, in the p-n junction, and now the charge carrier has to flow the outside circuit. So, both p side and n side of the semiconductor should be connected through a conducting path, all right. So, generally in n side semiconductor, if you see a solar cell, there are gridded contacts, grid kind of contacts which are quite good and transparent. It allows light to fall, and it also gives a very good electric current. Okay. And the bottom is generally, or the p side is generally a metallic contact. So, if I just look at it in terms of interfaces, I have a junction, this is the junction, and now I have one side, I have electrical contact, and other side I have another electrical contact. Now, what is the advantage of that, or what is this configuration? So, generally this junction which we consider, it is a semiconductor junction, and the electrical contacts are metallic. So, it is a junction of semiconductor and metal. So, semiconductor metal junctions are very important in semiconductor physics, and I think you might have studied the semiconductor metal junction or Schottky junction. I am not going to discuss in detail about the junction, but when we make such junction, this is a current which one observe. So, in that you see a term which is I naught. I naught is basically saturation current, I d is basically electric current in dark condition, and then small e is anyway it is electrical charge, k is a Boltzmann constant, n is ideality factor of the diode. Okay. One can also in a little bit of with modification, where you can consider for slightly higher voltage V, this term is more than 1, then I d or dark current becomes I naught exponentially V by n k t. Okay. So, if you take a log of that, then one can get a straight line of that. So, what are the outcomes of this particular analysis? The particular analysis actually is done in order to get some quantities. So, what are the quantities that you can get from this particular equation? The quantities which you get from this particular equation is n, that is ideality factor, and then you get phi b, which is contact potential. Okay. So, now the question is what is phi b or what is the contact potential? The contact potential is basically a potential which is generated in metal and semiconductor junction. Let me just show you how this contact potential is formed. Suppose you have a metal, okay, and metal, this is Fermi level and this is say the vacuum level. So, this is an energy which is metal work function. So, this is metal side, and if we see a semiconductor side, then vacuum level and conduction band maxima, and this is valence band. Okay. So, vacuum level and conduction band, this difference is called chi, which is electron affinity. So, contact potential is basically a difference of work function of metal and the electron affinity value of a semiconductor. So, that is what you can get from this equation, and the other quantities which you can get, because it is a typical IV characteristic. So, for a typical IV characteristic, let me just draw it here. For a typical IV characteristic of a diode, this is voltage, this is current, and this is forward bias and this is reverse bias. Okay. What one can get here, R s, and in the reverse side with what one can get is R s h. So, other quantities which you get from the analysis of this equation is R s is the series resistance and R s h is the shunt resistance. So, what are the quantities that I get as analysis of these? One is series resistance, another is shunt resistance, and one is ideality factor, and another is contact potential. So, these are four important physical quantities which one can determine by analyzing this IV characteristic or dark IV characteristic. Okay. Now, we shine light on this particular circuit. So, when I shine light on this particular circuit, it is something like when you bias a diode. So, as soon as the light falls on it, lot of photo generated charge carriers will be there, and it will make another current component which flows exactly opposite to the current which we have seen in the dark condition. So, this is a typical circuit. Now, you can see now this is the current source, this is the diode which is basically the solar cell, this is the series resistance and this is the shunt resistance, and you generate voltage across a load here. So, in this circuit, if we analyze the IV characteristic, typically you can see the IV characteristic exactly like this. Okay. So, look at this IV characteristic and follow this what we exactly are looking at. So, as I mentioned you that when we shine light, that is a current of the diode under illumination, it basically it is the dark current minus some short circuit current. What is short circuit current? Short circuit current is a current when your applied voltage is 0, that is the circuit is shorted. Okay. So, if I follow this particular line, if you follow this red line, this is basically the IV characteristic when it is illuminated, and this was your previous dark characteristic. So, what are the quantities you obtain? You can obtain few important quantities. One is VMIM point, that is maximum power point MPP from this graph. You can shade this entire area which you can see here, and this area gives you a quantity which is known as fill factor or FF, and then you have two important electrical quantity. One is short circuit current ISC or JSC, which is ISC by the area, that is short circuit current density, and another important quantity is open circuit voltage VOC. Okay. Open circuit voltage VOC. Okay, that is when the circuit is open. You have maximum voltage you generate from a solar cell is VOC, that is open circuit voltage when current is 0. So, these are important quantities. So, now I have already shown you when we analyze the dark characteristic, we got 4 important quantities, that is N, phi B, RS and RSH. Okay. Ideality factor, contact potential, series resistance and shunt resistance. Okay. These are the 4 important quantities which we got when we analyzed dark current or dark IV characteristic. And now, from this illuminated IV characteristics or IV characteristic under illumination, what are the quantities we got? We got the maximum power point, and then we got fill factor, we have ISC short circuit current or JSC short circuit current density and VOC. So, these are actually important quantities which we get from the analysis of illuminated solar cell or from the circuit which is actual under operation under sunlight, actual operation under sunlight. Okay. And these are the quantities which we will see in entire photovoltaics, whatever we will study, we will see that we will look around this quantity always. What is the maximum power point? What is the fill factor of a solar cell? What is the short circuit current density? And what is the open circuit voltage? Okay. So, suppose you extend little bit of this equation and just try to determine what is open circuit voltage. Okay. Open circuit voltage is anyway voltage when current is 0, and if you just make a little bit of modification of this, you see this is the open circuit voltage. So, open circuit voltage depends on ideality factor N, it depends on contact potential phi B, it depends on short circuit current density JSC. These are the 3 quantities which control open circuit voltage. Okay. So, now how it controls? Ideality factor controls open circuit voltage, because when you say increase the ideality factor, how do I increase ideality factor? In ideal case, ideality factor of a diode is 1 when the electron flow is only a thermionic process. You might have studied in semiconductor physics. Okay. But if we have more lot of recombination and generation centers and there are some defect sites or defect locations, then there will be lot of recombination and generation process which will make the ideality factor higher. Okay. So, this is a trade off between this recombination and generation as well as the thermionic emission. So, typically the ideality factor varies from a range 1 to 2 in a solar cell. So, now see another quantity, that is contact potential phi B. I have already defined contact potential when we make a metal and semiconductor junction, and the contact potential, if it can be enhanced, okay, that is a sort of material fabrication process. If you can enhance a little bit of contact potential, maybe some another layer you put in between, then you can have a higher VOC. And another is JSC, that is short circuit current density. So, how do you increase short circuit current density? you can increase short circuit current density by generating more and more charge carriers. That means more and more light absorption leads to more and more charge carrier generation, which eventually leads to more and more short circuit current or short circuit current density, and it also increases open circuit voltage. Okay? And this is the final equation which we always look for in a solar cell. So, what is the final equation? Final equation is basically when I calculate the power of a solar cell, multiply current and voltage, and this is the power at maximum power point Pm, where maximum current and maximum voltage that we have seen in our previous slide, and then fill factor can be defined as a ratio of maximum power, that is Vm cross Im, divided by the short circuit and open circuit voltage. When we multiply these two quantities, that is called fill factor. Okay. And now we define a quantity which is efficiency of the cell. Efficiency of the cell is defined as the maximum power or maximum power density divided by the incident power. And finally, we have the equation for efficiency which we use in solar cell. So, if you look at the efficiency, it is actually proportional to the short circuit current density, it is proportional to the open circuit voltage, it is proportional to fill factor. So, what we need in a solar cell, what is the goal of solar cell is to increase this efficiency. And if we have to increase, if we want to increase this efficiency, we have to increase short circuit current density, we have to increase open circuit voltage, and we have to increase fill factor. And these are the challenges. Okay. So, this basic circuit analysis tells us that one can have a better solar cell in terms of its performance, in terms of its efficiency, if we can improve these quantities, the basic electrical quantities like short circuit current density, open circuit voltage, etc., and fill factor, etc. Okay. So, now I will just come to one important point, that is called recombination process. What is recombination process? A recombination process is a process which actually does not allow charges to flow. So, when an electron and positive ions are generated, as I have shown in my previous slide, if they recombine, because always negative and positive ion attracts each other and they can recombine, this is their natural tendency. Okay. So, if they recombine, then they do not flow, if they do not flow, they cannot produce voltage. Okay. So, this is an issue which we have to look at, that what are the recombination process that take place. So, one recombination we can understand is a recombination which is band to band recombination. So, if I just have this conduction band and valence band, and if I have a charge carrier generation, electron and positive ion here, and if they recombine, if they fall, suppose before I take them away, they just attract each other and fall. This is a typical band to band recombination. But one can have recombination if we have say defect state in the or defect center, they act as recombination center. Okay. So, in the defect state, this electron and hole can be recombined, and this is known as Shockley-Reed-Hall recombination, and this is extremely important. So, therefore, when we want to make a material ideal for solar cell, we want to design a material ideal material for solar cell, what is important is that we have to minimize this Shockley-Reed-Hall recombination, or we have to see that how much recombination center should be there, optimized recombination should be there in terms of the fabrication of the material and in terms of the generation of charge carriers. Okay. So, there is an important trade off, and this is the second component. Third component is Auger recombination. What is Auger recombination? In case of Auger recombination, what happens when an electron is generated from say valence band to conduction band, and then electron is flowing, it is not coming out. Instead of coming out, it goes and excites another electron. So, that means it is lost in generation of another electron, which is known as Auger electron. Okay. So, the first electron is already lost. So, that is called Auger recombination process. So, now if we combine all these three recombination process, it actually recombination R for a charge carrier delta n, and if we make a quantity tau, that is lifetime, then I can have a combination of all these recombination process. And then how much a charge carrier can diffuse through? A charge carrier can diffuse through a relation d is equal to capital D tau to the power half. That means, the diffusion coefficient of in that particular material which is under study, and the charge carrier lifetime. Okay. So, let me just look at the basic design of a solar cell. So, if you please see that how this solar cell is the basic design of a solar cell. Again, what I mentioned, you can see this is p-n junction. P-n junction is this n-type solar cell, n-type silicon, this is p-type silicon, and this is a p-n junction, and on top of that we have an anti-reflective coating. I will just come to this point, what is anti-reflective coating, and then these are the metal contacts, and then on top of that there is a glass cover, and the bottom there is a metal backing. So, I have already analyzed this particular this structure, and I have already shown you how mathematically one can analyze this particular solar cell. So, if you connect one electrical appliance, say a bulb from this, and if you generate the the charge carriers here and allow them to flow through this, it works as a load and it glows. So, that means you generate power. Okay. So, just before I finish, I will just make a comment on what is known as anti-reflection coating. So, what is anti-reflection coating and why it is important? Anti-reflection coating is important because when light falls on a silicon surface, what happens? All light do not go inside. That means, silicon cannot absorb the entire light. All light cannot go to the another side. That means, silicon cannot transmit the all light, the entire light which is falling on it. Only a fraction of light or photons it can absorb. Rest of photons actually go back, that is reflected. So, and this is a big problem because silicon the reflection is quite high. So, now we have to minimize that reflection. So, what is required is to coat something on top of silicon that I have shown in the previous diagram, that a thin layer of some compound, typically say silicon nitride, silicon dioxide people use, a thin layer of that material which actually does not allow light to go back, that is anti-reflection. It allows light to go inside, it allows light to move inside, so that it gets absorbed. And how it is possible? Look at this diagram. In this diagram it is very nicely illustrated. So, when light falls here, if there is a destructive interference, there is no reflected wave, and if there is a constructive interference, that entire light gets reflected. We do not want that. We do not want the entire light should go reflect. This is an ideal case. So, what we need? We need a kind of destructive interference where there is minimum number of photons gets reflected, and this is the condition, this is the thickness which one is to maintain. So, these are the three layers. N0 is the refractive index of the air from where this photon is falling, and N1 is the refractive index of the anti-reflection coating which is there on top of silicon, N2 is the refractive index of the silicon which is a real material, and if this relation is satisfied, sorry, this is N1, d is equal to lambda by 4 N1, we get a proper destructive interference and it works like very good anti-reflection coating, where N1 is defined as N naught, this is this, into N2 to the power half. So, I can design this anti-reflection coating. So, when I design the anti-reflection coating, I choose the refractive index of anti-reflection coating using this formula, N1 is equal to N naught N2 to the power half, and then I choose the thickness of the anti-reflection coating, d is equal to lambda by 4 N1. Okay. Lambda is the particular wavelength which I want to absorb inside the material, or does not want that particular wavelength should be reflected. And then if you see that people have worked on various anti-reflection coating, they have started with bare silicon and they have coated with different anti-reflection coating, single layer, double layer, and then you can see this is wavelength versus reflection coefficient percentage. And when we consider bare silicon, the reflection is quite high. If you look at the percentage, it is almost 60% reflection, and if you see this particular end, it is still more than 30 to 35% reflection. So, light gets reflected back. Now, as soon as you use an anti-reflection coating, this falls. Okay. So, you can see for a range of wavelength, the reflection is almost 0 or reflection is minimum, and that is the importance of anti-reflection coating. One can have double layer anti-reflection coating, which is the third one, and you can have reflection minima for a broad range. Okay. And then one can also have textured silicon surface. The meaning is that you can make some kind of morphology on the silicon surface, and then you can additionally you can have an anti-reflection coating, and you can have better and better anti-reflection. So, in order to make a silicon solar cell with better performance and better efficiency, one needs a good anti-reflection coating. Okay. So, if I just summarize the lecture, what I have discussed so far, first we have started with the importance of photovoltaics or importance of solar cell. We discussed about some of the application of solar cell or some of the application of photovoltaic technology. We discussed about the challenges of solar cell. We discussed about a small junction solar cell with silicon. We discussed about various generations of solar cell, and then what we have discussed that how a simple junction or PN junction works as solar cell, and how one can generate charge carriers, one can allow this charge carrier to move in the circuit, one generates power, and then what is the electrical quantities that is important for a solar cell, like what we have determined from dark characteristic. We have seen that one can determine the ideality factor, contact potential, series resistance, shunt resistance which have lot of influence on the solar cell properties, which we will see in future, and every time we analyze a solar cell you will see these quantities will come. And then when we studied the illuminated solar cell, then we have a slightly different IV characteristics, and from these IV characteristics what we have found is open circuit voltage, short circuit current, we have found fill factor and the efficiency of a solar cell. Okay. Then we discussed about a simple configuration of a silicon solar cell with anti-reflection coating and the working principle of that simple configuration homojunction silicon solar cell, and then what is the basic fundamental physics or the process optical process that goes on in an anti-reflection coating to make an efficient solar cell and to make the performance of the solar cell better. Okay, so today we stop here, and in the next class I will discuss about more about the technological aspects of the solar cell fabrication, and then one very important solar cell, that is known as plasmonic solar cell. Okay. Fine, thank you.